5.2 volume. We'll start with remembering the formula for volume of a cylinder with base radius r and height h. So the volume of circular cylinder, because the base is a circle, is area of the base, which is pi r squared times the height. Now, if the base is not a circle, could be anything. Let's see, this solid we also call cylinder, right cylinder. And let's say the area of the base is B and the height is H. The volume is still area of the base times the height. So as long as we know the area of the base, then we can find, and the height, we can find the volume. So we have a solid S that is not a cylinder. So for solid S, that is not a cylinder, and it's not something we know the formula for volume of, so for a solid S that is not a cylinder, we have to derive a formula for calculating the volume. So we first cut S into pieces. We first cut S into pieces. So think about a loaf of bread, and you put on a counter and start cutting the slices of bread. So we're going to cut S into pieces and approximate each piece. Think about each slice of bread with a cylinder. So each slice of bread is not a perfect cylinder. We're approximating it with a cylinder. Then we're gonna add the volumes of all cylinders and take the limit of the sum. So if we have a loaf of bread and we slice it into, let's say, 20 pieces, 20 slices, that will be a rough approximation. But if we slice it to n pieces and let n go to infinity, then we're going to have exactly the volume of the solid S. So in other words, the volume of a solid would be the limit of this sum of n slices, so n goes to infinity, or we can say that's the same thing, that the maximum of the thickness of each slice, delta xi, goes to 0. So that means the slices are so thin that their width is almost 0. And so how do we find volume of a cylinder? We have area of the base, which I'm going to use the function x of xi star, that's area of the base, where we slice the particular slice, and the star indicates that we can have this interval. So the interval is from A, which is x0, to B, which is xn. So think about the slice of bread is that long, and we're dividing it into smaller intervals. And in each interval, we are picking xi. So somewhere here, that will be x1 star, x2 star, and that's where we calculate the area. Okay, so we multiply the area of the base here by the height. So the height of each cylinder is delta x. we can have it the same delta xi or just delta x. So that is integral from a to b, a of x dx. So a of x is our function that represents the area of the base of each slice, which is different. So that's why it's a function. So this is our formula for volume of a solid that is from A to B, and the cross section is a function a of x. So example, with something familiar, we're going to show that the volume of the sphere with radius r is, show that the volume of the sphere with radius r is v equals 4/3 pi r to the third. So for convenience, we're going to put the sphere with its center at the origin. So project the sphere. Oops, that didn't look good. Okay, here you go. So this is our sphere with radius r, so this is r, and a random point right here will have a radius r as well. So if we project here, we have, that's the point x, and this is the y coordinate. So the sphere is centered at the origin, and if we have a slice, if we slice the sphere vertically like this, the cross section is a circle. So if we slice it vertically, the cross section is a circle. I'm going to write this down. That's very important. The cross section is a circle with radius. Okay, so the radius of the cross section is this blue line. Okay, and that is y. Okay, so the cross section has a radius, it's a circle with a radius y. And what is y equal to? Since x and y on the circle, then they satisfy the equation of a circle, which is x squared plus y squared equals r squared. Then y would equal to square root of r squared minus x squared. So if you solve for y from the equation of a circle. So next thing we need to do is determine our cross section, a of x, which is our function that goes into the integral. Our cross section is the area of a circle with a radius y. So the formula is pi r squared, but r is y. So pi y squared. And now we're going to substitute y with square root r squared minus x squared, and then you square that, and we simplify, so it's pi r squared minus x squared. So this is our cross section, or the area of the cross section. So you notice we could have sliced this sphere anywhere, and that formula will be the same, whether the point is here, where I picked it in the first quadrant, or in the second, or anywhere else. This will be the formula for the cross section. Now x changes, so x, we're going to see it's from negative r to r as we're slicing that sphere. So by definition, the volume of a sphere or a solid is integral from a to b, a of x, which is the area of the cross section, dx. So dx here plays the role of delta x that we have here, which is the thickness or the height of our cylinder. So think about this green circle being the base. I'm gonna draw a picture here. Let's see. Think about this slice will have a thickness. So it will look like this, like a cylinder, like a cylinder. So let's continue with our formula here and substitute a and b. So we're slicing from negative r to r. And the area, a sub x, we determined earlier, it's pi r squared minus x squared dx. So for convenience, we can write that this integral is equal to 2 times integral from 0 to r. Sphere is symmetrical, so if we find half of it, slice only from 0 to r, this is 0 here, and multiply by 2, will be easier to calculate this integral. All right, so 2 pi is a constant. I'll pull it out. And what we have is integral 0 to r squared minus x squared dx. I'm going to break this down into 2 integrals. So integral r squared dx from 0 to r minus integral x squared dx from 0 to r. And this is 2 pi. So r squared is a constant. So we're going to pull it on the front, and then we have integral of 1, which is just x, evaluate from 0 to r, minus integral of x squared is x to the third over 3, evaluate from 0 to r. You can evaluate each one separately like I do, or all together. So that's 2 pi r to the third here, minus r to the third over 3. The rest of the terms will be 0, and that's equal to exactly 4/3 pi r to the third, which is our familiar formula for volume of a sphere. Another example. Find the volume of the solid obtained by rotating Find the volume of the solid obtained by rotating about the x-axis. The region under the curve y equals square root of x from 0 to 1. So we don't have the solid yet. We have to sketch it. First, we're going to sketch the region. So our function is y equals square root of x, which looks like this. It's in the first quadrant. We're from 0 to 1. So our region is this. I can highlight the region. It's like a little triangle with a curved side. So now we have to show the solid. I'm going to draw it again. So the region first, which looks like this, from 0 to 1, we're rotating around the x-axis. So here's the image. And I need to show that this is solid. So the base is circle. Okay, maybe I should use black here. So this is our solid. Now, let's take a random point anywhere on the curve, and that is a point xy, and slice it. So if we slice it, we always slice with a plane perpendicular to the axis of rotation. So the axis of rotation is the x-axis. My plane, slicing plane, will be perpendicular to the x or parallel to the y. So here's the slice, and it is a circle. And if you want to see it like a solid, you can see it. It is actually a cylinder, sideways cylinder. So this is delta x. This is the height of the cylinder. So here, let me show you the cross section. So this is the cross section. It is a circle. Now I'm showing the slice at a random point xy. So we need to always write down what the cross section is. So in this case, the cross section is a circle. And that's a good thing because we know the area of a circle. So the area of this circle would be pi r squared. But what is the radius? So the radius of our circle in the cross section is right here. So this is the radius. And as you can see that, I should write this down. Cross cross-section is a circle with radius equals to y. That's the y coordinate, but y is equal to square root of x because our point xy is on the curve y equals square root of x. So if this is our radius, square root of x, then the area, a sub x, would be pi r squared, or square root of x squared, which is pi x. And now the volume of a solid will be integral, and let's write the formula first. Area of the cross-section dx from A to B. What is A to B for our case? How are we slicing? We're slicing along the x-axis from 0 to 1. We have the formula, that's pi x dx, and very easy to integrate. This end up equal to pi over 2. Another example. Find the volume of the solid obtained by rotating obtained by rotating the region bounded by y equals x to the third, y equals 8, and x equals 0 about the y-axis. So that's a little different because we're rotating about the y-axis this time. Let's show the region first. So the region is determined from the graph of y equals x to the third, which is, we just need this part since we are from 0 to 8. And let's say 8 is over here. So from 0 to 8, x equals 0. This is the y-axis. So here's our region. Our region is this area, is this triangle with a curved side. So now I have to show the solid. Right next to it, I'm gonna sketch the region again and then rotate it, it says around the y-axis. So if we do that, this is the symmetrical region, and show it's actually a solid. So the base is a circle. So pick a random point in the region on the curve right here. So that's our random point xy, and slice it. We say we always slice with the plane perpendicular to the axis of rotation. So y is the axis of rotation. That's what it says. So we're going to slice perpendicular, and when we do that, a cross section would be a circle again, and we can show here that that is delta y. This times the height of our cylinder. We are approximating this section or this slice with a cylinder. It's not an actual cylinder, but if you think that delta y is really, really small, then it is approximately a cylinder. Okay, so let's write down that the cross section is again a circle with radius. Okay, let's show the radius. The radius is this. This is the radius, which is equal to the x coordinate of the random point. So the radius r is x, but we need to have everything in terms of y if our thickness is delta y. So how do we write x in terms of y? From the equation. So this curve over here, it's y equals x to the third, which if we solve for x, is cube root of y. So this is our radius, cube root of y. Now let's write a sub y. Everything's coming in terms of y now, if we're rotating around the y-axis. So a sub y, area of a circle, is pi r squared. So that is pi cube root of y, and then squared, which is pi y to the 2/3. So now we're ready to find the volume. That is integral from a to b. So how are we slicing here? This is 0 and this is 8. We're slicing along the y-axis from 0 to 8, and a sub y dy, that's from 0 to 8. We have the formula pi y to the 2/3 dy. And after you evaluate this, you get 96 pi over 5. That's the exact volume of our solid. Another example where now the region is between two curves. So the region R enclosed by the curves, y equals x and y equals x squared, is rotating about the x-axis. Find the volume of the resulting solid. So picture of the region. One of the curves is y equals x line and y equals x squared, the parabola. Where they intersect, you can actually set up a system to see where they intersect. So intersection of the two curves, y equals x squared, substitute, x equals x squared minus x equals 0, x minus 1 equals 0. So they intersect at x equals 1 and x equals 0. Or if you want to write this as pairs, 0, 0 and 1, 1. So these are the points, we knew that, 0, 0, and this is 1, 1, the points where these two curves intersect, and this is our region. So it's a little sliver. Okay, now let's show the solid. I'm going to sketch the same region again. And then the symmetrical region with respect to the x-axis is this, and show this actually solid. So we have a circle here. And this point right here is 1. Okay, so what is the cross section? If we slice this anywhere, so pick a random point and slice the solid, the cross section is not going to be a circle, but a washer or a ring. So let's write this down. Our cross section in this case is a washer or a ring. So a washer or a ring looks like this. It has an inner radius and an outer radius. So it has the inner radius, which is small, and the outer radius, which is big. So let's call the inner one R1 and the outer one R2. So our washer has inner radius R1, call it inner radius. R1, which is equal to what? That's what we need to determine. So the inner radius or the small radius is right here. I'll use a green. This is the small inner radius, and that's a random point xy. So it is equal to the y coordinate. However, we are on the curve x squared. So that is equal to y, which is x squared. All right, maybe I should write down y first. Y, which is equal to x squared. Now the outer radius which is R2, is also equal to y, okay? But it's a different y, because this y over here, xy random point, this y is on the line y equals x, so this y is equal to x. So now a of x, this is the area of the cross section. How do we find area of a washer? So here is the washer. Obviously, we're gonna find the area of the outer circle minus the area of the inner circle. So we're gonna have pi x squared, which is the area of the pi x squared, that's pi r squared, so that's the area of the outer circle, minus pi. Now the inner radius was x squared, and then we have to square it. So this is the area of the washer, factor out pi x squared minus x to the fourth. So don't be alarmed that x squared has to be bigger than x to the fourth. That is true because we are from 0 to 1. So from 0 to 1, x squared is bigger than x to the fourth, and this is positive. So now the volume should equal to integral from 0 to 1. As we're slicing this solid, we're slicing it from 0 to 1. So these are boundaries. A sub x dx. Everything is in terms of x because we're rotating around the x-axis or a horizontal axis. And now we have to substitute our a of x, which is pi x squared minus x to the fourth dx. Evaluate this. I suppose we can evaluate this. So that will be pi, I'll factor it out, x to the third over 3 minus x to the 5 over fifth. And we're evaluating this from 0 to 1. So you should get 2 pi over 15. So final example. So far, we're rotating either around x-axis or y-axis. But that's not always the case. We can rotate it around different axes. So find the volume of the solid obtained by rotating the region in previous example. So the same region as before, about the line y equals 2. So we're going to have the same region as before, and let's sketch that region. So we need lots of rooms above. So this is the x and this is the y-axis. And I'm going to have the region, it's from 0 to 1. It was between the straight line and the curve. So this is our crescent. This was our region. I'll shade it here. And our line is y equals 2. So if this is 1, then this is 2. This is the line of rotation. So we need to draw symmetrical, and I need more room here. All right, so we have to go over. So this is our region right here. Perhaps I can do this. Right, erase it and make this bigger. So okay, so we had here about the line y equals 2. So the symmetrical region would be over here like that. And we can highlight it too. So we can see the solid. We'll have a circle here and another circle here. So it's shallow inside. I'm going to show here a cross section. So a cross section, if you slice this solid anywhere, so random point, you slice it, you're gonna have a cross section that is a washer, okay? So the cross section is a washer or a ring, and we need the inner radius and outer radius. So we have to show that it's not as simple as before. I'm going to use the cross section over here. Okay, so this is the inner and the outer circle. All right, so the outer circle, the outer radius is this one. Let's call it R2. That's the bigger radius. And this is a random point where we're slicing. It's a random point XY. So that's a random point XY. And the inner radius is this one. So that is R1. So this is the big problem in this kind of problem, is to determine the inner and the outer radius. So I'm going to say that the inner radius is 2 minus x. And we're going to look in the picture and see if that's the case. The inner 2 minus x. Why? So we know from here to here is 2. So all the way down is 2. Okay, so a random point where we're slicing right here, that is xy. So, and we're on the line y equals x. So this is 2, and then from here, perhaps I should demonstrate this here. This distance here is x. So our radius is 2 minus x. Okay, why is it x? Well, it's actually x equals y because we're on the line y equals x. The outer radius is equal to 2 minus x squared. Okay, so again, all the way down to here is 2, and x squared is y. So now finally we can write the area of the cross section, which is pi outer radius 2 minus x squared minus pi inner radius 2 minus x squared. So we're basically doing pi r squared minus pi r squared, but with different radii. And so that is equal to pi. And then if we do the algebra and FOIL and combine like terms, x to the fourth minus 5x squared plus 4x. And finally our integral. So integral from 0 to 1, a of x dx is equal to integral 0 to 1 pi x to the fourth minus 5x squared plus 4x dx, which is easy to integrate, 815 pi. So a quick summary for our formulas. Formulas for volume. The volume of a solid is equal to integral a to b a of x dx, or the volume can be integral c to d a of y dy if we are rotating around the y-axis or a vertical axis. So in the first case, a of x is the cross-sectional area. In terms of x, and a of y is the cross-sectional area, but in terms of y. So these are the two formulas. And the cross-section can be a circle. So if the cross-section is a circle, whether it's a of x or a of y, then the area of a circle is pi r squared. So the cross-section is a circle, then a is equal to pi r squared. You just have to determine what the radius is. And if the cross-section is a washer or a ring, then we have another formula. If the cross-section is a washer or a ring, then the area is, whether it's in terms of x or in terms of y, I'm going to write it in both cases. The area is equal to pi outer radius squared minus pi inner radius squared. And that concludes this video.